All right, so here we are this evening. We're going to work through a replication of what we did last week with our GPS practice downloads, if you remember that. So some of the things that we needed for this lab. Once again, the purpose of this lab, before we get started, actually, let me backpedal a little bit, was to collect areas or to capture an elevation survey with use of our Garmin GPS units. And so I don't have one up front here, but when it comes down to data collection, I may borrow one of yours after you download your data. The purpose was to collect elevation and XY data in latitude, longitude. And what we are going to do is compare our results of our elevation map, just like what we did for total station. We're going to compare our GPS elevation map to that of our total station. So, and discuss some of the differences. Again, up on the border, we said big categories in our reports are looking at error, elaborations, conveying clarity in our meaning, in our writing. But in order to do this lab, a couple of things we will need. One will be your Garmin GPS, which we were just outside, and we collected waypoints from A, B, C up through however many number of points we had. We also collected a track log. And all of those points that we collected, both waypoints and track logs, will contain an X and a Y coordinate, which is our latitude, longitude basically, and then a Z field as well, which is our altitude. And based on what our demo was last week with our DNR GPS offload program, the default units for our altitude are in meters. So our elevation that we will reference or be referencing in this particular lab will be in meters and not feet. So we'll also need, so we have one, our GPS. Two, we're going to need our offload cables. So if you have your data offload cables for your GPS, pull those out, get those handy, and plug those into the back of your GPS units. So make sure that one end of the port is in the back of your GPS unit, and the other portion, which would be the USB, could be plugged into your computer now, or we can wait a few minutes. It doesn't really matter. And so to that end, we walked through last week, if I pull up my files here just as a refresher, and I think we all went through this, but underneath our handouts directory, I will navigate into our spatial data collection folder, and under week 5, we had a special program in there that we used, and that was called the DNR GPS. It was that zip folder. Remember that one? So we used the DNR zip folder, and we extracted, let me just open this up here. Whoops, here, let me back up. Not where we want it to be, but let's come down here and let's see if we can. Inside of that zip folder was that DNR GPS folder, and we said the file that we were interested in extracting was the DNR executable, the EXE. So we double-clicked on this file right here, that EXE, and then that ran an install for us for all of our DNR GPS utilities necessary for this lab. And so when that was finished running, we ended up with this icon right here. And that icon would have originally been saved in the location that you extracted all those zip files to. So I think I maybe extracted mine to the C10 folder originally. And then all I did was I right-clicked on this file in my C10. That's where I saved it. And then I said, send this shortcut to the desktop. And that's why it's on the desktop here. Nevertheless, this icon is the one that we will use to initiate our point offload. So with your USB plugged into your computer and the other end plugged into your GPS, let's go ahead and turn on your GPS device. So turn on your GPS, everyone, if it's not already on. And again, I will have to borrow someone's once we go through the process. Problem, okay. Okay, so up front here, Lou gave me her GPS to try, so I plugged in my GPS, the USB and everything. Now what I'm going to do, if you're interested in following along, or if you are ahead, that's fine too, based on last week's demo. All I did was I activated or double-clicked on my DNR GPS shortcut. It looks like a small-scale GPS unit. And some of the menu options across the top we explored. And one of the things that we looked at here in order to be successfully connected to that of your GPS was we looked at right below the File Edit GPS Waypoint menu options. You'll see where it says Garmin, eTrex, Legend, H, so on and so forth. That communicates to you that the program has successfully connected to your GPS. If it did not, we went under GPS last week and we said find GPS. And if we did that, it will run through all the different ports in the computer and what's connected to your GPS and ultimately find it for you, essentially. But being that we did this last week, I think it's a relative quick connect. The other thing that's indicative of a good connection is this big green button down here where it says connected. Presume the green means go. We're good to go type of thing. Is there a projection? No, there is not. We collected all of our data this evening with latitude, longitude, spherical coordinates, no projection. So what do we do next? Well, let's first download our waypoints. So we collected waypoints and tracks up here. Let's go down to waypoints and then download. Download complete. Okay, so there's A, B, C, D, E, F, G, up through J. And other labs, other classes might be different, but we had up through J here. So I'm going to select this cell up here in the upper left to highlight all of my waypoints. Now I'm going to go to File, Save To. You can either say Arcmap, File, or File up here. It doesn't really matter, but Arcmap, File, and a 2D shapefile. So I'm going to save this one. We'll call it Lou. This was Lou's data, so we'll call it Lou's waypoints. But call yours something else. You might call yours waypoints. I don't know. And make sure it's in a file. Again, we said no space names. No spaces in your path directory. So for me, once again here, I'm going to double check where mine is being saved to, and mine is under the C drive here, and then GIS615A, and under the GPS folder, and that's where I'm going to be saving mine. But you'll notice there's no spaces in there. It's just C drive / GIS615 / GPS. So I'm saving my points right here, my waypoints. All right, so those were extracted successfully. Now what I'm going to do is go to my tracks. So let's go ahead and go over to the track menu drop down, and let's select download. And it might take a few moments. But here it looks like there were 1,225 points that were contained within our track log. How many did some of you obtain? 900. 900. So it all depends on how long. You know, we had our GPS unit set up to acquire 1 point every second. So when we were moving every second, it was collecting a point. But in here, you'll notice in this waypoint attribute list, if you will, you'll see the latitude, the longitude. These are all attribute samples, or all attribute information that will move over to your shapefile. In other words, what we see here will become the new attribute table for your new point feature that we generate. we particularly are interested in this altitude column right here, because this will become, for us, our Z that we will use to create our elevation surface inside of Arcmap. But other attributes here that will be brought over will be the timestamp, the model, and some of these other things are available if we were maybe doing depth studies like bathymetry or something like that, or temperature for streams or water bodies or something like that if we had temperature devices. But the rest of these not particularly valuable. If we had a comment field, you could certainly add in if something was a drain field here or a fire hydrant or whatever, but not necessary really for us anyhow. But I'm going to select all of these and I'm going to save those just like we did before, Arcmap, and then to File. And I'll call this one track log. This is Lou's track log, and then save. What do you think? What do we want here? Absolutely, a point. Lines would be crazy if that was all. It would be lines all over the place. But we're interested in points so that we can generate an elevation surface off of those individual points. So let's select point. And it's saved those out. So now what I can do is minimize this or close it out. And let's go ahead and look in Arcmap. So go ahead and open up an Arcmap session. And while you're at it, you may want to open up an Arc Catalog session if you wish. Otherwise, for me, I might just use my Arc Catalog tab over here on the right-hand side of my Arcmap session to check out all of my data and folder connections where I'm already connected. If you do need to connect to a folder, once again, we will use this Connect to Folder button and simply navigate to the folder that you wish to connect to and proceed from there. But since I'm already connected, I'll move over into my GPS folder where I just saved and offloaded these two particular files. Either I can select these and drag them over or drag them into my map, or I can add them from my Add Data button up here. And since we were using the Add Data button in the past, I think I'll remain in following suit with that to be able to download, or I'm sorry, add data from our folders. So Lou track log, I'm gonna add one at a time here just so we can see what's going on. Some things to pay attention to right now. Let's look at our lower right-hand portion of our screen. We have unknown units, and that is to be expected. We don't have any data in there. However, when we add our waypoints, what do you expect those to look like? Feet?
Oh, meters.
You sure?
But when we collect data, it's feet.
Well, think of how are we collecting our data on our GPS units? That would be really ultimately in latitude, longitude. But it will show up for us on your decimal degrees, which is sort of a planar. Remember last time we talked about spherical is latitude, longitude, but when we convert those to decimal degrees, let's load those in here. You'll see that, now look at our lower right-hand portion of our screen. They show up as decimal degrees, so they're planar coordinates. So they're trying to be almost flattened out, a planar based. And we said, well, once we're west of the prime meridian, which we are here in the US, that's where we end up with our negative on there. That's why we see that negative 91. On here, negative 91, so. Anyhow, there we are with some of our data points. Let's go ahead and explore our attribute table. One of our great rules that we always speak about is explore your data. What data do I have? How can I use it? What data or what information do I need more of? The only way we can do that is by exploring our data. We did that a little bit in our DNR GPS utility. However, here, it's purely a replication of that. And so for us, the main thing that we really need in this case here is our altitude. It's always a good idea to check these though. You know, when we're dealing with decimal degree data, our decimals should only be 2 points in. And our longitude should always be 91, negative 91, in this particular area here of Minnesota, because we're west of the prime meridian, like I said there, and our decimals purely reflect the changing from the spherical to planar coordinates. And then our altitude here is in meters over here. So this attribute table, someone asked the question before, well, could we include this in our lab write-up? I said, sure. You could take this and export this if you wanted to. You could export this as a just under the table drop down up here. You could export this or run a report. But if we exported this out, for example, it would be as a database file. We could open that up in Notepad or Excel or whatever it is that we wanted to. But there are different ways to export this out if we wanted to. We could also edit this attribute table. We could delete fields or columns here. For example, we could remove display. We could remove proximity, distance, symbol, color. You could remove all of those if you wanted. And we've gone through that, how to edit tables and whatnot. You know, to add fields or to delete fields. We're able to do that just by right-clicking here. You know, if we wanted to remove this, we could delete it. But it all depends, whatever you want to do. Again, we work with a purpose. That's the idea. If it's purposeful to remove columns, remove attributes, and they're not really practical, or we don't need them, remove them. But if you may need them at some point, you know, keep them and make a copy backup of your data and work off of that. So I'm going to leave these right here as they are. Okay. Now let's go ahead and add the track log points. I just want to add data, and I'm going to add lose track logs. Ooh, look at that. I'm going to make the waypoints just a little bit larger, just for color so we can see this. So all the points in purple that you see on the screen, those are our individual points. And if we look at waypoints, there are some useful things for us, our identification. So if we wanted to label this field, which we can do, I'll do that for now. So I'm going to go into the waypoints and under properties. And then under the labels tab up here. And the string that I'm interested in labeling would be certainly not any of these. I'm trying to, was it the ident field?
Yep.
I think so, if I remember right. So the identification field, basically. So I want to label all my points in purple with the identification column. Just to show you what that is there, I want to label everything with A, B, C, D, and so on and so forth. That's what that's telling us. Okay. So now I'm going to label those features. So I can label them from right-clicking on the waypoints, either right here, label features, or I can go under properties and label them right from under my labels tab here, where it says label features. Either one. And you can see that they're labeled A, B, C. Let's turn off our track log for a minute. So here right away, you can see how goofy some of these points look. Lou, is this how the road really looked? A and B was over here, and C and G, D, E, F, G, A. This doesn't look too bad, you know, right here necessarily. We have some funny business going on there. These are all excellent examples, not just for Lou, but for you all when you first see your waypoints, to think about this. Error. Outside, we spoke about different things impacting data collection, especially for GPS, which one was what, James? Sure, could be atmospheric error. What was another one we talked about? The building was right next to us, so it was essentially limiting our horizontal plane access.
I think that affected mine because on my map, my tracking points kind of stop like where my H is, and I don't have any from when I went all the way over up against the
Sure,
wall.
doesn't surprise me. Anytime we're working along obstructions, but that's why we're doing this lab, to show you all the things that can impact our data. What was another source of error? So we had buildings, trees, weather, maybe clouds, atmospheric error. So tonight when we wrap this lab up, we're going to learn about, I'll reinforce some of those things that you probably are reading about already, such as atmospheric error, what we define as multipath error, buildings, trees, things like that. So all of those things impact the accuracy of our data, because we certainly, the road we know probably followed suit more A, B, C, and then D and E, and then crossed over to F. It's more like a road should look. Here, these points aren't too bad right here, though. All right. So there are the track logs of everything there as well. One thing that we tried to do last week that might be particularly helpful for you is we went over back and forth about a process called project on the fly. And we stated that it was crucial that all of our data have what's called a definition. And so I'm going to just show you here, integrity, how to get through and examine the definition of layers. And we said this a little bit before we're ready. We'll learn about this in other classes. However, one of the keys for us in this general and source tab, rather, is that this information right here, I'm inside, first off, layer properties, and then under the source tab. In particular, what I'm interested in looking at is right here. This, to me, gives me a lot of valuable information. Why? Well, it tells me right off the bat that the data that you collected, that we all collected if we're using your device, all the data was collected in geographic coordinates. Latitude, longitude, essentially, decimal degrees here, with a WGS, basically satellite-based data, 1984. That's fine. It's a common default. So this is a definition that goes with the data. Think of it like a table of contents for a book that you're reading. So you open up a book. What am I going to read about? Well, here's my table of contents. If the table of contents were missing, it would be very challenging for you to understand what you're going to read about. It's no different than what the software is doing for you. The software, when using Project on the fly, is going to read this definition first. It's going to look at the table of contents. It's going to say, okay, both of these have the same definition, the track log and the waypoints. It said, all right, I'm going to set this data frame view, in other words, what we're looking at, all to that of WGS84. So any other data that you add in here, even if it's not geographic coordinates or GCS WGS84, even if it's not this, the software will try to read the table of contents of that data. It will read its definition if it's there. And if it's correct, it will be able to project on the fly to match our data. Sometimes the problem, however, is that other data is not defined, or it's defined incorrectly. If something's not defined, or if it's defined incorrectly, it will not project on the fly for you, because the table of contents are either missing, or they're the wrong table of contents for the wrong book, if that makes sense. This creates a problem for us as analysts using data, simply for the fact that project on the fly can be very misleading, as we learned last week. It could take data and project it into something for which it really is not correctly represented in. So the good news is, and you will learn about this in other classes, in particular advanced GIS, that we have a coordinate system with a definition that is accurate. So that is a good thing. So with that being said, we went up under File, and then Add Data, and we went to Base Maps. So File, Add Data, Add Base Map. And I believe that well, I'm not sure what the default is. I'd have to look. I don't want to say anything for sure on that. What we explored last week was looking at data and sort of streaming the base layer, if you will, into latitude, longitude. And we were looking at distortion. So we're just streaming a lot of data in here. And so there are lose points. Obviously, the Science and Learning Center building is omitted from this graphic here, being that it was a year or so old. However, we can see some of lose points on here. Some of them are probably not too bad, generally speaking. But as we look at this, I do want to maybe at least highlight and demo this out for everybody once again, is that one of the things we were really interested in looking at last week was this preservation and distortion, and why people typically work in a projected coordinate system is that so that it preserves, so that the coordinate system or the projection preserves any distortion that may occur in directions or distances, angles or scales, etc. And so I would like to illustrate that before we move on. I don't know if it's a necessary step, but sometimes when we're working with raster data, in other words, trying to create an elevation surface off of this, off of the decimal degree data, I would highly recommend it, because raster data, the data that you generated, for example, with total station, what that does for us is it makes data in a square or a rectangle. And all of the data that's contained, and we have sections of this in advanced GIS that deal only with raster data, and I love it. It's a great thing. But think of raster data like a great big screen that's full of different cells containing different values. And those values for us are going to be elevation. In this case, it's going to be our altitude in our meters. So every single one of these cells will have a slightly different value that represents an elevation for us. But to that end, these cells have to have a dimension. And in many cases, raster operations work much better if you have a projected data source. Right now, we are not projected. We are just in decimal degrees, no projection. So what that means is, how do we assign a decimal degree cell size for mapping? It's really tough. I mean, you can do it. It'll generate it, I think. But it may be better to first project our data into something more usable on a 2D, so like a piece of paper, so that we can minimize distortion and we're not trying to map surfaces with raster data. It's just not as clean. Does that make sense? So instead of having decimal degree length and width here for all of our cells, we're going to convert that into something maybe meters based, so that our altitude, which our GPS collected was in meters, right? We will take this data and convert it into a projection that has an XY, horizontal, into meters as well. Then we're in meters all around the board. Make sense? Okay, let's do that. This is our next step. And we did this last week too, so if you are comfortable forging ahead, please do so. What I'm going to do is I'm going to say up here under catalog, and I'm recording all this as well. So if you miss any of this, it'll be right available for you on Integrity as well. Or at least it says it is here. So underneath the toolboxes here, I'm going to go under Systems Toolboxes. Again, this is from last week. Under System Toolboxes, And we'll go down here to data management. So under system toolboxes, data management. And this would be something that you may want to do for a final project as well. If you're interested in using GPS that we're collecting, you'll probably want to project your data out. So you'll probably want to repeat this if you're using GPS. Under data management. And then, where do we go next, do you think? You recall? Projections, yeah. Projections and transformations. We'll learn more about transformations next semester. It's a yawn of excitement. All right, I'm just teasing. Okay, you notice that there are two things here that you see. One is define projection. The other one is, it says project. What do you think the differences between those are? The defined projection means that we are writing the outline or the table of contents to a book. Remember we talked about how books can have wrong table of contents or outlines? This is a place where you can set that. So if something's incorrect or it was never included, you can add your table of contents to a book. However, we better make sure that it's correct. So if it's incorrect, we're essentially giving someone a book with the wrong table of contents, wrong outline.
So we use define projection to change the project.
To change the definition only, to change the table of contents. We're not changing how long the book is, we're not changing the content, we're just changing
the project. Projection.
Yeah, with the defined projection, we're not changing anything physical about the book. All we're changing is the outline. But we need to make sure that's correct. However, we know our data is correct as it is now. It's the correct table of contents for the book. The data is right. The table of contents supports it. The project tool is the one we want. The project tool physically changes the book. It makes it lengthier, shorter, changes the color. Maybe it's wide, more wide than it was narrow, but it physically changes the data. It's essentially taking our data that was in latitude, longitude, and we're going to mathematically change the XY location of that data. So project. Do not confuse those two. Define only changes the table of contents. We want to physically change our book. Make it thicker, skinnier, different color. We don't need to rewrite the table of contents. The table of contents are correct. We're just changing our book. Changing a publisher. They may want to put a new cover on it. We're just going to update it. So with the project tool active, what do you think we'd want to put into here? Let's try our waypoints first. We'll do our waypoints and we can go back and repeat with our track log. I'm going to add in your waypoints and our input coordinate system, our table of contents, if you will, our GCSW-GS84 is our satellite-based datum. That's good. Now let's go ahead and save this to an output directory. That's what the next step is right here, where it says output dataset or feature class. So I'm going to say, all right, well, I'm just going to give my book a new name now. Instead of GPS 101, it's going to be GPS 101 Edition 2. Changing the book. So Lou, we will say Lou waypoints projected. As a reminder, shapefiles or feature classes can generally have longer titles, but raster data has a limit to, I believe, around 13 characters. Typically is what it has historically liked. So remember that when we're generating our rasters, elevations, slopes, things like that, we want to try to keep our names shorter, or it may truncate it for us. The software will. So Lou, waypoints projected. And I'm going to set mine to UTM, Universal Transverse Mercator here. So that UTM is just a reminder for me, that's UTM. But you don't have to do that, just a thing for me. Okay, now the output coordinate system. Here's one that, being that most of us are just getting started here, we're not going to know a lot about projections yet, and that's okay. That stuff will come. However, one of the things for us that we will want to pay particular attention to would be that thinking about what folder do we want to? Do we want another geographic coordinate system, which basically means kind of an unprojected, or do we want a projected?
Projected.
Projected, yeah. So just like last week, went into projected coordinate systems. Do you remember what we selected? UTM. And UTM stands for Universal Transverse Mercator. And Mercator projections, like we said last time, act to preserve bands. So in North America here, we'll have these bands. And it's kind of like making a slice, if you had, it's almost Halloween time there, but if you're slicing a pumpkin all the way around, all those bands are being preserved along those reaches from north to south. And so we're interested in the most recent version of that, which is the North American datum. We spoke of those datums, that they're datums for all over the world. When we look at high elevations, low elevations, combined with those mathematical horizontal surfaces, where they meet, where they best match, mathematically helps us to define a good datum for data that we may want to use as a reference surface for that particular part of the world. So under NAD 83 here, our zone, our slice of that pumpkin, if you will, 15, right. This information right here is sort of our new table of contents to our new book. That's what this means for us right now. And once we project the data out, we will be able to go under Properties and our Source tab and see our new table of contents. This is going to be very important because if we use this data and we add it to a new data frame, or we try to project this on the fly, the software will need to have this in order to make a project on the fly. So let's go ahead and select OK. James, do you have a question too?
Yeah, well, I was just going to ask, I see that the WGS 1984 is down there. Would it be the same, would it give us the same projection as we already had before?
Under UTM here?
Or down, or right there, WGS.
Yeah, I mean, that's more of a satellite-based data. I mean, you could certainly, I mathematically would not know the difference between what that is. There are slight differences, definitely, but from our standpoint here, would it be a noticeable difference? Probably not. Not when we're considering 10, 12 feet of horizontal error. But let's select OK, and then OK again here. So we should have something that looks like this. And down below it will say that it projected your data successfully. If it gave you the green check mark, said it's good. Since I just did my waypoints, I'm also going to project my track log at the same time since I'm in here. So I'm going to go over to my catalog and say project again. I'm just going to repeat the process. Project, track log. I'll move through this one pretty quickly since we just did the waypoints and that's fresh in your mind. So Lou track log projected UTM. Okay. Coordinate system, I will use the same. So under projected, UTM, NAD 83, zone 15. That's our pumpkin slice where we are here in this. Then OK. But there are all sorts of projections you can use. Some are in feet, some are in meters. Again, one of the reasons we're using this one. It's quite common, but it also retains the XY units in meters. So that'll reflect well for us with our altitude in meters off our GPS. Who's excited about this? Good, thank you, James. Good. Carrie's excited. We're all excited. Okay. So we're giving you a lot with this lab. Some more extras than what we commonly do, but at least it's better to be aware of it. Now, this moved over and projected okay. What I'm going to do is go up here and say insert new data frame. Remember, the first layer that we add to a data frame, ArcGIS always defaults to that table of contents to try to match everything else up to. And right now, no matter what we do, everything is going to be in decimal degrees. So let's add a new data frame.
But do we need to project the base map?
Nope, it should do that for us on the fly. The base map is streamed from ArcGIS. I want to believe that that's in decimal degrees anyway, or like a lat long, latitude, longitude, I believe, but I can't be certain. So we cannot project that imagery. Some imagery you can if you own it and you have tiled imagery, you can, but this is all being streamed from ArcGIS.
And it suits all the projection. I mean, the base map, like we can choose a different projection for the points in the track, but all these projection is suitable for the base map.
Yeah, the same thing would happen with the base map. That would have a table of contents. Because that base map has a table of contents, and you have all of your data that you added into your ArcGIS session, the software is going to read that base map's table of contents, and it's going to project it to match whatever you have. But that's why it's so important that you always have the right table of contents for the book, your data. All right, let's go ahead and add in here the track log and the waypoints. I just wanted to add data. You can add them one at a time or both. Make this larger. What do you see in the lower right-hand portion of your screen right now?
Meters.
Meters. That's a good sign. Down here, we have meters. So that tells me that there was a successful projection of our book. Our book was changed. The dimensions, the mathematics, the dimensions of it were changed. The content didn't change. It's all there. The data's all there. It's just that we changed the dimensions of the book. Table of contents was updated successfully. Let's go ahead and add, under File, let's add data. Let's add a base map. Okay, under File, Add Data, Add Base Map. Let's add our imagery. So Lou, to your point, this now should project on the fly, right? So it's reading the imagery or the base map definition, and it's projecting it on the fly. And did it do that? Number one, yeah. Otherwise we wouldn't see it there. But two, we have our meters and our projection preserved down here in the lower right-hand portion of our screen right here. So we see our image, our base map, we see our data, and we see our newly projected data. I'm going to zoom out a little bit here. Just using this zoom out button a couple of times. It's taking a while to catch up. Okay, one of the things that we looked at last week was distortion. You remember how we went from decimal degrees to projected data? Let's look at that. Right now, this data frame is in UTM Projection. Let's label that so that you can see it. This is in the UTM Projection right here. We checked it. We know that because our coordinates have changed here. And up above up here, this was in decimal degrees. You don't have to change these. I'm just typing it in here. So if you go back through Tegrity, you can make some sense of what I'm doing here. And so what I'm going to do is right now our UTM is active. What I'm going to do right now is come back up to decimal degrees to this data frame, and I'm going to activate that. You can do that by right-clicking on this heading up here where it says decimal degrees for me, and say activate. Now I'm going to turn off my track log. I'm going to try to get at about a similar scale. Now all I'm going to do, you could sit and watch. All I'm going to do is toggle back and forth between these, and what I'd like to have you recognize is the shift or some of the perceived distortion that's going on between decimal degrees, which we have right here. It says in our lower right-hand corner, decimal degrees, and that of our UTM. So just want you to watch this. I'm approximately at the same scale. So we're just toggling back and forth. It's a little bit from planar or projected to decimal degrees. Can you see that? How things are just changing. It's almost like a warp a little bit. Yep.
How to add the base map for the second data frame? I forgot.
Okay. The question was, how do I add a base map? Under File, and Add Data, and then Add Base Map. And there are quite an assortment of different base maps that you may choose to select to add to your Arcmap session. For example, let's say we were looking at topo maps this evening. There are different types of topo maps that you might want to add. There are imagery with labels, streets, and there might be a couple of others here as well. So you might find a particularly valuable base map for some of your data collection for your final project in this course, for example. So again, it always comes down to what is your purpose? What is your purpose? Your data collection methodology should be consistent, should also align with your purpose. It should not be the other way around. That's where we get into trouble. When technology drives the purpose, or when our preferences or our own biases drive a purpose. That's not really a good thing. We're automatically building in bias and more error into our entire process as a result. Okay, now what I'm going to do is I don't want to work in decimal degrees any longer, especially if I'm going to be creating raster data from that, in which case I need to make sure that those cells are able to be mappable. So I'm going to activate my UTM projection. So I'm in meters, and that shows us down here in the lower right. We're in meters. And I'm going to turn on lose projected tracks there as well. And the waypoints that I collected right here, or that Lou collected, that you all collected, I'm not worried about making those into elevation points at this time. All I wanted you to collect those for so that you could include those on a map or a graphic. But instead, we will generate our elevation surface off of your track logs. All right? So inside of the track log, you'll notice that we have an attribute table in here as well. I don't think you really need to include all of this in your lab write-up. You might just take a small, nicely organized, clean screenshot, take it into Paint, clip it out, and if you wanted to show an example or a sample of it, that would be plenty appropriate. So let's go ahead and I'm going to zoom in here a little bit more. And I'm going to focus just on the track log to work with. So just like we did last week and the week prior, I'm going to begin a process to make our elevation map. So we're creating a raster data set that will be of elevation. So Lou, here's what we will see what your data looks like. So under catalog, I'm going to move down below in the systems toolboxes. So I'm still at my system toolbox level. And I'm interested in the spatial analyst tools. Just like you've been doing already. Spatial analyst tools. Where do we go from here? Yep, let's go to interpolation. Interpolation. And we can select Spline, or IDW is fine too. So I'm using Spline. Spline is a generic interpolation function that is generally pretty good for elevations or when you're looking at gradual changes in something. If you're like water or pollution or water table elevation, something like that is probably good. It may not be particularly useful when you're looking for maybe different outliers or points that may be really dependent upon others. But I enjoy using it for the fact in this case that it's a general representation of elevation patterns that are gradually changing. So points, I'm going to use my track logs, or Lou's track log. And what should I select for my Z field? Altitude. Whenever we are generating a raster layer, you'll notice that all of these have something in common. They're all set as a numeric field. In other words, they need numbers, not letters. They need numbers so that they can generate cell values over here. That's why when it's a Z value field, it's always going to ask you for numbers. That's why if you're ever collecting data and why we selected our in total station, our elevation columns, remember we set those as floating point? Those are numeric so that we can map them as a Z field. So altitude. All right, let's go ahead and save this. Now remember, we're creating a raster, so we really shouldn't exceed 13 characters. Ah, good, yep. So we'll want to keep this shorter. So we will call this Lou underbar LEV. That's what I'm calling this. This is just Lou's data. So you could call your own. You could call your own elevation, GPS elevation, whatever you want to call it. And I'm calling this one. Let's see, 1, 2, 3, 4, 5, 6, 7. I'll call it GPS elevation. That way, Lou, if something ever messes up on your computer, it's all stored on this one. All right. Here is an example of this cell size. What that, by my cursor on your screen, what the 0.1928 means, that means this. It means that each cell size that's going to be created in our data will be this big. So 0.1, almost 0.2 meters. You can change that if you want to, but keep in mind, the larger you make that cell size, the more granular your data is going to be. Meaning, it's going to be less accurate. The smaller the cell size, the more accurate those individual cell values can be. Not necessarily more accurate, but they'll give you your data a better perception rather than being so granular and grainy. For right now, I'm just going to leave this as the default. Sometimes I change these. It depends on the units that I'm working in the size of the area that I'm working in. However, in this instance right here, I think it's perfectly acceptable to leave this as a default in meters for our work. Okay, the rest of it we can accept, and okay. Okay. I'm going to turn off my imagery here. And you do not need to have imagery on this at all for any reason if you don't want to. The reason we put that on there to begin with was to show you about how the project on the fly works and working with projected data and distortions. So again, you do not need to have imagery with this unless you so wish. Okay. Does anyone else's look like this? Lou's should look exactly like this. But I would expect that all of yours would look different. Because every instant that you're out there collecting data, everyone's data should look different. That's because of that randomized Z. That Z, the Z value, a common expectation for your Z accuracy will be at least a minimum of 1.5 to 2 times the horizontal accuracy. In this case, it might even be more. So that means we could be off by 2 times, I'd say maybe 50 feet off of what it really would be. So imagine trying to take elevations and you're 50 feet up or down from where you really should be. Good luck in trying to create a topographic surface off of that. 50 feet, that's a long ways. Up or down. With our total station, how much were we off with that? Tiny amounts. Tiny. GPS is about 1,000 times this difference of accuracy, of error. Because of that vertical. Remember I said we can't get a reading from down below us? That's why the Z is so inconsistent and so incorrect. So we're also getting some really interesting numbers up here. And for example, this -15. And this is because we just, again, one, the building is sitting here. And we don't know what's happening down there. So this is what's creating some of these ranges in our data to be wrong. Not wrong, it's just the software is trying to predict what's happening out here, but we don't have any data. It was a building, for that matter. So I was working with one person this week on how do we extract out, basically trim this stuff off so it doesn't impact our data range. Here it said in white that we're almost up to 580 some meters. That's really, really high. And this is really, really low. It's like we're down in a hole somewhere. So how can we sort of trim this off there? We're going to show you a trick to do that. Do you need to do this? No, but I think it would make your visualization a lot more effective, especially when we're talking about this. Conveying clarity. Conveying a clear story. Here are some things that you can do to make this a little bit more informative. All right, again, we're going into some other classes here, but I think it's definitely okay because this isn't telling us a lot. I wasn't sure what the results were going to be, frankly. But most of our data that we're interested in is in this tan band right here. And I'm going to show you that we are dealing with rasters. I'm going to zoom in on this small area. If I keep zooming in more and more and more, eventually we're going to get to small little cells. And now these cells are going to be super tiny because our cell size was, I may not even be able to see it here. But inside of it, these are all small little cells. And all of these cells, for example, if I'm just clicking, where's my info button here? Here it is. So if I'm clicking here in tan, this tells me that this particular cell is 228.16 meters. Now I'm going to go right over here. Now it's different. This is 231. I'm going to go here. All these cells, you can see those numbers, those elevations down here changing. It's because of all those little cells in there. They all have values in meters. Should be shown how to make a mask. Want to learn how to make a mask? It's fun. Why not? Take us maybe 10 minutes. Okay, so what I'm going to do is let's turn off our elevation. And what I'm going to do is turn on all my points. And for me, I'm particularly going to be interested in preserving the areas of interest that fall within my area of study. So we're going to create a new shapefile to sort of enforce the area we want to generate elevation data for. So let's go into our catalog. We're really giving you a lot of extra stuff here, but the best part, this is all integrity. You can go back and watch it, every single step. So in our Arcmap session here in catalog, what I'm going to do is right click on my folder and say new shapefile. I just right clicked up here on the folder I want to save my new shapefile in. I'm going to say new shapefile. All right. And polygon. We want to select a polygon or create a polygon so that we can contain the elevations inside of our data. So we want a polygon. And we're going to call this one here my poly underbar mask. It doesn't matter necessarily what you call it. All I'm trying to communicate to myself is that I'm creating a polygon to be used for a processing mask. Okay. The coordinate system, you could add that as a UTM if you wanted. However, it's going to assume the same coordinate system of the data we have already projected. So I'm going to say OK. And now what we can do is start editing our poly mask, or whatever it was that you created here. So I'm going to make sure that my poly mask is selected. Those buttons there. So I'm editing over here, and I'm interested in creating some straight line segments. What I would recommend is on your data set, yours will look different than mine or Lou's. So what I'd like to have you do is start on a particular point on the outer edges and make a polygon that goes around the outermost points. You may have to select through a few of them, I don't know. But get a general polygon that goes outside of your points. And I'll start off here and try to do the best I can for Lou's here. But we may want to start with something like this. You may have to select a few of them. I don't know how the process will go for you. But just make sure all of your points fall within that polygon. Simple as that. So you don't have to select every single one. Did I finish sketch here? I need to get back in here and okay, and so all of you might have something that looks a little bit different, but to begin the process, once again, I had to restart there, but it was simply to use your straight line segment. You can see and left click to begin, and essentially you're just going to left click at each of these points so long as you capture the outermost points. So for example, in here, I didn't need to trace around those because it's contained within my boundary. It's found inside of here. So I'm not really concerned with that. So, but I am trying to capture my outermost boundaries And in particular, when you see that I'm over here, I was able to select and then just simply go up to the next outer boundary. So in effect, what this mask is going to do is we are going to extract out, when we generate our elevation, all the elevation that's found to be within this blue line, so within our polygon. That's the objective for what we were trying to do. So now I'm going to save edits and stop editing. And I've just made a mask, or I'm sorry, a polygon for which I want to control my elevation. So I just want elevation inside of here. Make sense for everybody there? What we're trying to do? Yes? Okay. All right, next step then is I'm going over to our catalog. And once again, I'm going into my system toolboxes right here. System toolboxes, and then I'm going under, I believe it's data conversion. Let me check that out. And it is. So under conversion tools. So in conversion, the reason that we're in conversion is we are going to change our polymask layer, or your polygon that you just made. You're going to change that into a bunch of cells, raster cells. So we'll be able to use raster data and raster data. And we're almost done. We're almost done. A couple more minutes here. So let's go down where the toolbox where it says to raster. In other words, we're going to take a polygon and we're going to convert it to a raster. So I'm going to open this box up right here under to raster. And what do you think we want in there? What tool? If you have it open on your computer there, what do you think? Under
Polygon raster.
Yeah, you bet. Polygon to raster. Let's open up this tool right here. Polygon to raster. Input features. Well, let us use our polygon that we just made. That's the only polygon we have in our table of contents. Our value field, again, this is going to look at something numeric. However, we don't really care this time what this is, because all we're using it for is a general layer to process underneath. But I'll use the ID. There's really only going to be one ID, and it's going to be the polygon ID. So simple as that. So ID. Let's give this a name. When I say give this a name, I mean we're going to give our new raster data set a name. So I will call this one my mask. That's what I'm naming this. My processing mask. So once again, no spaces in your path name. No spaces right here in your path name. And keep your raster name under 13 characters. So for me, I'm calling mine a mask. Everything else, I'm going to leave as default. My cell size, of course, is going to relate nicely to my 0.19 default cell size I created with my spline interpolation before too. So we're going to leave that alone. Now let's say OK. Let's go ahead and turn off our poly mask. Actually, you could probably delete your polygon layer now. So I'm going to remove my polygon layer. I'm going to remove my vector layer. There's two types of data that we're going to work with in GIS, and it's either going to be in vector format, which that's all we've been doing so far, except when we started to generate our elevation surfaces. Those are raster data sets. You're going to see those in future classes. Those are the two data sets we're going to work in. One is very accurate, being the vectors and the points and things like that, or lines. The more generalized surfaces are not as accurate, however, they're very necessary. So when you look at the weather at night, or on your phone, or you look at rainfall totals, those are raster data sets generated in weather, or temperature, snowfall. You cannot physically measure every square meter to obtain all the snowfall or all the rain in those areas. So raster data sets are a necessity. They're very valuable for analysis purposes. I'm going to remove this, my mask. I don't need that anymore. Instead, what I've created is my processing mask that I'm going to use to extract out my elevation data. Here's where the fun begins now. Essentially, what we're going to do is to regenerate our elevation surface. So the LU underbar GPS elevation, I'm just going to redo that. So I'm going to delete this. I don't need my elevation surface in there anymore either. I'm going to remove that. So the only thing I have in here are my waypoints, my track log, and my new raster processing mask. Let's zoom in on here just for a second. Here are all those cells. So all the little cells that are created as part of our raster data set. Just to show you. Okay, what should we do now? Well, there are a couple things we can do. And up under where it says the geoprocessing menu, let's go ahead and select that. Geoprocessing. Actually, what did we do the other day? We did extract by mask. We can do this. We can do it. That's fine. Let's go under environments here. You don't have to do this particular part here. But it might make sense for you. And the processing extent under environmental settings, I'm setting to my mask. That means that the extent of all the data that I'm going to be generating for my new elevation is going to only go to the extent of my green mask underneath here. That's what that means. So it's a processing mask. And let's select OK. You don't have to do this step. It's just a fail-safe in case things don't work. Now let's go under Catalog, and I'm going to close out my conversion tools. And let's go back down to Spatial Analyst Tools. We're going to use a new tool that's called, under the extraction toolbar, or the extraction tools right here. We're going to say extract by mask. So extract by mask right here. I'm under the spatial analyst tools, not under interpolation yet. Well, let's see here. So we're going to say, being that we set our processing window up here under our environments, our processing extent was set to our mask, we shouldn't need to do anything except rerun. We don't need to extract by mask. We can certainly do it, but let's go back to what we're familiar with, interpolation, and then spline. Let's run a spline. And so when we run that spline right now, let's use our track log, just as what we've done before, no problem. And our altitude for our Z value field. I'm going to give this a new name, our output raster. I'll call that, I'm going to write over my original layer here. Well, maybe not here. We'll call it number 2. So LU GPS elevation 2. And then I'm going to select save. Leave everything else as it is. So track log, altitude for my Z value field, and then OK. And being that we set our, okay, that's odd. Why did it do that here? Reset. That should have set our extent to our mask, but that's okay. We have another approach to use. Just wanted to check that. Okay, well, that being the case, one final step. Here we are. Under Spatial Analyst Tools, under the extraction tools here, we're going to use extract by mask. This I know will work. So once again, I was under Spatial Analyst Tools, Spatial Analyst Tools up here, Extraction, Extract by Mask. That's what we have. Input raster, I'm going to select our elevation. We have right here. Now I'm going to drop in our mask layer. So it's kind of like a cookie cutter, I tell people. A cookie cutter approach. Say if you ever made cookies and you had the cookie dough and you use your little cookie cutter, it trims out everything else that you don't want and it keeps the area inside of your cookie cutter. That's what we're using our mask for. So if we turn, let me move this down. That's the same thing what we're doing here. Is we're saying, all right, I have my cookie dough. Up here is my input raster. And then my cookie cutter is my mask, which is this raster layer that we created off of our polygon. And when we run this software, I want you to trim all this other stuff off and just keep everything inside of my cookie cutter. So I'm going to give this a name. I'm going to call this Lou Final Elevation. That might be too much. Lou Final GPS. That should work. So, okay, no spaces, under 13 characters, and then OK. All right. So now, what we end up with is essentially a elevation map of our data. Now, we can certainly, by right-clicking here and looking under our properties, under the symbology, here we can change that. We can change this to more an elevation, color ramp, if you're interested in that. You know, this kind of shows a really goofy combination, but again, what we have are all these little cells in here. You can see these cells, but the range of our GPS altitude, that's what we're looking at in there. So 261 all the way down to 175. If you zoom in, you can see all these cells. All of them have a different value of elevation in meters. So Lou, we have some wild things going on here. If you do not like how this looks, this is definitely not a bad thing. It just shows you the range in your altitude. We can still change that, or we can change that yet again by simply changing to a classified scheme, and that will band everything out for us. So let's try that under classified. And we can add in, I don't know, 15 or 10 different classes if you want. My color ramp for elevation, I always like to use this one right here. It's more for elevations. And that sort of gives us a different way of looking at that, but it's showing us all of our areas. And for example, this darker red color here might be between that 220, what's that, brown? Oh no, 224 and 227 meters. So that's quite a shift. But again, it's the accuracy of our Z values. So at least what you have right now is kind of interesting in that if you wanted your base map imagery underneath that, we can make this transparent if you want. For example, if we made our GPS transparent under properties, under our display, we can set our transparency here, for example, to 50. I'm under layer properties, underneath my elevation, and apply and OK. But I mean, we can still regulate our display. It's how we're communicating, sharing different things. So I gave you a lot of extras here tonight, and at the expense of some other things, but these are going to serve you very, very well in other classes too. Any questions about what we did here? Again, this is all recorded so that you can go back to it at any time and see what we did. Any questions about this at all? Was everyone able to get their GPS data loaded? Okay. What I'll do now then is the report format for this lab would be the same as what we've been doing for all of them. You know, and what I would maybe recommend is including a snapshot of this and comparing it with your total station. If you're really interested in feeling ambitious, you can check out Arcscene, which you could put this into something three-dimensionally, which will look really, really odd because the data is so all over the place.
What was it?
Arcscene?
Arcscene.
Yeah, if you want to. It would be cool if you wanted to try that, but it would be this program right here. Did I go over it? Yeah, where is that? Arcscene. Here it is, right here. Arcscene. So you can load this into Arcscene and practice adjusting some of the heights, and it will be pretty ugly looking in there. This one would be because our Z values are so poor.
So can we put like transit state, no, the total station map into the Arcscene?
Yeah, I mean you could. Yeah, you could. Yeah.
As long as it's raster.
Yeah. Well, you're right. Right. Well, you could put two-dimensional data in there too. It's about creating surfaces and use the help function, or for example, look up at Google how to add data into Arcscene. We can do it now if you want, although we're kind of running up on our time limit here. I don't know if folks had project questions there, but we can do that in another class too, so that's okay. Any other questions on this? Otherwise, I'll shut Integrity down here and we'll wrap up. Okay. This is GPS, a Garmin GPS, and how to use projections and masking for elevation mapping purposes.